Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week we are covering fluid mechanics. We have already entered into third lecture and this lecture belongs to Archimedes principle. In this lecture we will talk about the dynamics of a submerged body and we will also look into the equilibrium of floating body. Okay. So let's share our screen here. Okay. So in yesterday's class, we already started talking about Archimedes principle, but let me recap that again. So Archimedes principle simply says that if a body is fully or partially submerged in a liquid, let's say the liquid's density is rho. Okay, so this body is going to experience a force that will be equal and opposite of weight of displaced liquid. So let's say this is the displaced liquid and this force would be known as buoyancy. Okay, so it will be experiencing some buoyancy over there, and the buoyancy, the expression for buoyancy will be given as that would be negative of weight of displaced liquid displaced, you can say. Like for example, in this case, if the density of surrounding liquid is rho, okay, and its volume of this solid is v, and here we can say that this body is since fully submerged, so it will be displacing the liquid equal to its own volume. So in that case, the volume of displaced liquid will be V and the density of liquid is rho. So rho times V would be the mass of displaced liquid. Okay, and that multiplied with G will be giving you the weight and the negative of it. So for example, if the gravity is downward, so the buoyancy will be upward over here. So this relationship gives us the expression for buoyancy. And in yesterday's class also I mentioned, okay, like if the frame or if the container in which this all thing is kept, okay, is accelerated, then in this place of g effect, g, we will be using g effective over here. So let's, with the help of one example, let's try to demonstrate this fact. Okay, so let's say we have a container, okay, and some liquid is filled inside it, and this is accelerating with some acceleration a, and we have already learned that in this case this open surface of the liquid will be inclined, and this angle would be theta, and this angle we have already calculated. Okay, like theta would be equal to tan inverse a by g, etc. All these things we are aware of. So for example, if we are having a submerged body inside this liquid, okay, so what would be the magnitude and direction of the buoyancy in this case? So now you see, so first of all we need to find out the magnitude and direction of G effective. So magnitude and direction of G effective will be perpendicular to this surface. G effective and open surface are mutually perpendicular to each other. Okay, so in that case, the direction of G effective is in this direction. So the direction of buoyancy experienced by this body will be opposite to this. So this would be the direction of B effective, or B simply. So this B, the magnitude of this B will be given as, let's say the density of liquid is rho and the volume of the solid is V. So this would be rho times V times G effective, and you should realize the value of G effective in this case would be nothing but root under G square by a square. So this relationship is rho V into root under G square by G square plus a square under root. Okay, so The direction I have already shown. So like, let us recap how did we found out the value of G effective over here. So we can choose uh, like the weight of displaced liquid we have to find out. So let's say its mass is m. So mg would be acting on this in vertically downward direction, and the container is accelerating, so ma would be acting in leftward direction over here. So this would be the resultant net force experienced by this submerged body. So like that would be m times g effective. Okay, and this would be theta. So just by solving, you will be getting this theta and this g effective very, very simply. Okay, so please remember, the buoyancy does not act always in vertically upward direction. Rather, it would be acting in the direction opposite to the effective weight, or G effective, you can say. Okay, so now let's also understand the concept of effective weight. And being said that, let's look at one more example here. Like for example, we have a lift, and let's say we have a container. Okay, and in this some liquid is there, and this body is over here. Okay, and its volume is v and density of liquid is rho. Okay, so what would be buoyancy on this? If this container is accelerating vertically upward with acceleration a, okay, so in that case the g effective would be nothing but g plus a. So the buoyancy would be, in this case, b will be equal to rho v, and g effective in this case would be nothing but g plus a. And if this lift is accelerating downward, okay, and the container is here and this is the body, okay, in that case the buoyancy will be in this direction, and the magnitude of buoyancy would be rho times v times g effective here would be g minus a. Now you must realize, if this lift is freely falling, that means if a is equal to g, so in that case the effective buoyancy will be equal to 0. So that is one situation. Another case, let's talk about the effective weight concept. Okay, so say there is a container and it is filled with some liquid, and say this is a static container, and we have some spring balance, okay, attached to which this there is a block of mass m, okay, or you can say its weight is w. Okay, w will be equal to mg. So when this block is submerged into this liquid over here of density rho, okay, so what would be the effective weight of this block over here? So effective weight will be nothing but the tension in this string. So whatever the tension as measured by this spring balance, that would be our effective weight. And let's say also, say this liquid's density is rho l and this solid density is rho s over here. Okay, so we have to find out the effective weight. So when we will be drawing the free body diagram, so since right now this block is in equilibrium and we are interested in finding out the reading of spring balance, means tension we want to find out. So the forces acting on it is first of all its weight, okay, and we have already learned about buoyancy. So this body will be experiencing buoyancy in vertically upward direction. So balancing forces, we can simply say that T would be nothing but W minus B, and T we are saying it that is as W effective over here. So now you see, in order to find out W effective in terms of W only, W let's take common, and that would be 1 minus B by W. Now let's try to find out this ratio B by W. So B, definitely, let's say the volume of this block is V. So buoyancy would be nothing but rho L into V into G. So that would be the weight of displaced liquid. And its weight would be W, you can say, that would be mass of this block times G. So mass of this block would be simply, you can say, rho S into V into G. So obviously B by W, you can say B by W is equal to rho L by rho S, and substituting this value in this equation, W effective, we will be getting it as W into 1 minus rho L by rho S. Okay, so there, like, effective weight would be positive. Like, let's take condition like case 1. Okay, if rho L is smaller than rho S, then obviously W effective would be positive. Okay, and case 2, if rho L, density of the liquid, is greater than or equal to density of the solid, in that case, like, weight cannot be negative, you can say. So effective weight, you must be saying, that will be equal to 0. Like, it will be a net vertically downward force. Like, although if rho L is greater than rho S, but there is no weight of it, or if there is weight, you can assume that would be in vertically upward direction, effectively, you can say. So this is the case. So what will happen if, you can say, rho L is greater than rho S, then this body will start floating, and it will displace only the amount of liquid which will be sufficient enough only for balancing its weight, and in that case it will be in equilibrium. So effective weight will be equal to 0. We will discuss more about floating in the coming section. So this was the concept of effective weight. So with the concept of this effective weight, let's discuss one question here. Say we have a container filled with some liquid, and that has been kept over a platform, okay, which is kept over a spring balance. The reading of spring balance right now is equal to 1.5 kg. So now later on, what we did, we submerged some solid body suspended by some spring balance over here, or spring simply suspended by a spring. Okay, and this solid here has, let's say, mass is equal to 0.5 kg, and its volume is, say, or density, let's say density is 2000 kg per meter cube. So previously the reading of spring balance was equal to 1.5 kg. What would be the reading now of the spring balance? New reading of the spring balance we intend to find out. So how are we going to deal with this situation over here? So now, see, when we have submerged this block over here, so this block has come into the contact of liquid, so they will be exerting force on each other. Like, the liquid will exert buoyancy on this body in upward direction, so equal and opposite force will be exerted by the solid body on the liquid, and that would be B in vertically downward direction. That is basically action reaction pair. This arrow I have drawn is the force exerted by the liquid on this solid. So equal and opposite force that will be exerted by the solid on this liquid over here. So now if we consider the balance of or force balance on this system minus this block over here simply, so this system had previously mass equal to, like, or its weight was equal to, you can say its weight previously was equal to, since the initial reading was 1.5 kg, so its weight was 1.5 kgf, you can say. And the buoyancy that it would be acting, the buoyancy will be acting, or not, we should not say buoyancy, but the force would be equal to the magnitude of buoyancy. So B, and the B will be equal to here density of the liquid into volume of displaced liquid, uh, that must be in kgf. So density here is, you can say, let's say this is water over here, so that is 1000 kg per meter cube, and this v here is, you can say, mass is zero point 0.5, so mass upon density, that is 2000. So what we will be getting over here is 0.25 kgf. Okay, so the force exerted by the spring balance, you can say this force, which would be our new reading, that would be equal to w plus b. So that would be 1.5 kgf plus 0.25 kgf, so that is going to be 1.75 kgf over here. So this is our answer. Okay, so we have discussed the concept of effective weight, and here in this revision session I want to focus on the parts, okay, where generally student commit mistake and people are often confused in. So let's take one of those problems. Let's say we have a container, okay, and say it is filled with two different liquids, okay, of density rho 1 and rho 2, and some, for example, some cylindrical body is submerged in it, and for instance, let's say that is in equilibrium. So as you can see that this cylindrical body is partially in liquid of density rho 1 and partially in liquid of density rho 2. So let's say the volume in the liquid 1 is V1 and volume of the solid in liquid 2 is V2 over here. So now we are interested in finding out the net buoyancy. That is the first thing we want to find out. And the second thing we want to find out, that is force exerted by liquid 1 on the cylinder. And thirdly, we want to find out the force exerted by liquid 2 on the cylinder. Let's say this wall, this height h1 and this height h2 is given. Okay, so let's try to figure out the answer to this question. Although this question is very, very simple, because but I have taken this question because generally people commit mistake in answering that. So the buoyancy, simply, as we have discussed, that the buoyancy is equal to the net force exerted by the surrounding liquid, okay, on the submerged body, and that is equal to the weight of liquid displaced. So you can see directly that how much liquid 1 is displaced. So the liquid 1 that has been displaced over here, the mass of that liquid would be rho 1 times V1, and its weight would be simply G. And simply the weight of liquid displaced 2 is rho 2 V2 G. So this is simply buoyancy. So the confusing point is the people think that this term over here, rho 1 V1 G, is the force exerted by the liquid 1, and this rho 2 V2 G is the force exerted by the liquid 2. But that is not correct. So that is the confusion people generally have. Okay, although the net buoyancy is this quantity over here, and it is made up of these two terms, which look like this is due to the liquid 1 and this is due to the liquid 2, but these terms are not exactly the forces due to liquid 1 and liquid 2 over here. So now let's look closely. So the liquid 1, for example, will exert force on the cylinder through the contacts only. Now you see, like this liquid is going to exert pressure on this cylinder, horizontally from all around. And you must understand, like, these horizontal forces must cancel each other in order to consider this horizontal equilibrium. So no horizontal forces. So at this face, okay, at this vertical face of the cylinder, this liquid is exerting no force. So the liquid is exerting force. Liquid 1 is exerting force from the top only. Let's say that is F1. So we can find out the magnitude of F1 here. And let's say this height is H and the atmospheric pressure is P naught. So the pressure at this level, we can write it as P naught plus rho GH. And let's say cross sectional area of this cylinder is A. So what we can say, uh, V1 here we could have written in terms of um, A and H1 as rho 1 A H1 times G plus rho 2 A H2 times G. So now you see, like, F1 we are trying to calculate over here. So F1 will be equal to, F1 will be simply equal to uh, this pressure, that is P naught plus rho G H, okay, into this area over here. So that is the force exerted by liquid 1. So now let's say force exerted by liquid 2. Let's try to find out. So again we must say, like, the liquid 2 will not be exerting any force horizontally. Net force in horizontal direction is going to be equal to 0. So force exerted by this liquid on the vertical face of this cylinder is going to be 0. Okay, so the liquid will be exerting force through the bottom contact only, and the pressure over here is, you can say, that would be P naught plus rho 1 GH1 plus rho 2 GH2. Okay, so this force F2, we must say this force F2 is going to be the pressure over here, that is P naught. Here we must write rho 1. So P naught plus rho 1 G, and one term here would be rho 1 GH also, because we are measuring the pressure from the top. So that would be P naught plus rho 1 GH plus rho 1 GH1 plus rho 2 GH2. Okay, so this is the force. So the net force, again with the help of these two equations, so B will be equal to, you can say, net vertically upward force would be F2 minus F1. So, and that multiplied with A, you can say simply A. So this term over here will get cancelled with this, and this term over here will get cancelled with this term over here. So you can say, after subtracting, we will still be getting rho 1 GH1 plus rho 2 GH2 into A over here. So now you can see, like, the buoyancy is still the same value, but you must be very careful that this force, this part of the force, is not the force due to the liquid 1, and this part of the force is not the force due to liquid 2. Rather, force due to the liquid 1 and liquid 2 are these quantity, and liquid 1 will apply force effectively at the topmost surface, and liquid 2 will be applying force at the bottommost surface. Okay, so I hope, like, I have made myself clear in this question. Another problem I am going to take is again, one problem people are confused in. So let me take this problem. Let's say there is some container and a homogeneous liquid is filled inside this container, let's say of density rho, and there is some solid body submerged in this liquid, okay, which is made up of two different materials. Let's say their interface is plane and keeping horizontal. Let's say the volume of the upper part is V1 and the density of the upper part is rho 1. Okay, and similarly for the lower part, that is rho 2 and V2 over here. So obviously they are glued to each other. Like this part of the solid, the upper part of the solid and the lower part of the solid, they are made up of different materials and they have been glued together. So if they are glued, so that means there would be some gluing force. Okay, so that means like they will be exerting force on each other in equal and opposite direction, and we wish to find out the magnitude of that gluing force. Okay, so in order to do that, so let's look at the proceeding and the other data which are given in this question. Let's say this would be some this is plane surface and this area is A is given, and let's say this horizontal plane area is at depth h from the upper surface of liquid, and we wish to find out the gluing force. So for that, what we can do, first of all, we can write like the force balance on, let's say, upper part of the body, that is part 1. Okay, so if we will look at the forces, so let's say, so this part over here, so this part will experience what all forces. Now you see, so first of all would be its weight. Its weight is definitely, its density is rho1, its volume is v1, and g times g is its weight. So that is its weight. Okay, and like what would be, see, this is in contact with this liquid, the upper part of this solid is in contact with the liquid, and the liquid is applying force on it from all around. So will this force be equal to rho1 v1 uh, g? No, that will not be force. Like rho1 v1 g would have been the buoyancy. Okay, if only this part would have been surrounded by the liquid from all the sides. But you can say that here at this interface, the lower interface, the below this surface, at this surface, the liquid is not exerting any force. Okay, and below this part, this is solid. Okay, so what would be the force exerted by the liquid on the upper body, like that has been represented by the green arrow? Okay, so that we need to find out. So let me put this logic over here. The logic is, so if the solid, the upper part of the solid would have been surrounded by the liquid from all the sides, then the force exerted by the liquid must have been equal to rho1 v1 g, and that was equal to buoyancy. But it is now not in contact with the liquid from the bottom layer. Okay, so the liquid will no longer be exerting force on the bottom layer, which it would have otherwise applied. Okay, so what would be, if the liquid would have been at the bottom, what force it would have applied? That would have been the vertically upward direction. So that force would have been, you must understand, that must have been like the pressure at this level, you can say that would be rho g h. Okay, the pressure at this level is rho g h, and that multiplied by a would have been the force exerted by the liquid from the bottom face. So rho g h into a, force which would have acted if the liquid would have been below, but it is no longer acting. So from the buoyancy, we must subtract this quantity. From the buoyancy, we must subtract, this is pressure, so that multiplied with area, we must subtract this quantity from the buoyancy, so that would be the force exerted by the liquid over here. So the net the buoyancy, total buoyancy, you can say, if it would have been surrounded by liquid from all sides, the weight of displaced liquid would have been rho into v1 into g, and that we must subtract this quantity, so that would be rho g h into a. Okay, and since this body is in equilibrium and that has been kept by that gluing force fg, so obviously we can say this is, you can say, w1, and this you can say effective buoyancy on um, body 1. So Fg you can say would be nothing but Fg would be B1 minus W1 over here, and the value of B1 and W1 we have already found out. Similarly, we can do the force balance for the lower body, although we have found out, but this quantity similarly can be found out using the equilibrium of lower body. So let's do the equilibrium of lower body. So the lower body will experience a force due to liquid from all around. Okay, so let's discuss this dynamics. So its own weight is going to be rho 2 v2g. Okay, and it would experience a buoyancy in upward direction if it would have been surrounded by the liquid from all sides. The buoyancy would have been equal to rho v2g. Okay, but see, some like this force again, which would have been acted in downward direction, is no longer acting. Okay, so basically we need to add that force in that quantity in order to find out the force exerted by the liquid. So that would be going to be rho gh into A over here. And obviously the gluing force on the lower body will be in upward, vertically upward direction. So let's say this is B2 and this is W2. So in that case, Fg will be equal to W2 minus B2. So when you will check, like this quantity and this quantity are going to be same, provided like this thing is in equilibrium, like rho 1 V1 G plus rho 2 V2G is the weight of this body, and that must be equal to rho times V1 plus V2 times G. That is the net buoyancy on this body over here. Okay, so this was one question. So we have discussed some portion of the dynamics of submerged body. Now let's spend the remaining time in discussing the flotation. Okay, let's discuss the concept of flotation. So you must realize that when a body is floating, obviously it would be in equilibrium, so its weight will be balanced by buoyancy. That is, you must, like I already said, like its effective weight will be 0. Okay, and you must also realize this point is very, very important. Like if for a floating body its weight is balanced by the buoyancy, that means the weight or mass of displaced liquid will be equal to weight or mass of the floating body. And that is very, very important, although it seems very, very simple to understand, but this is very, very important. Okay, so when a body was fully submerged, okay, it displaced liquid equal to its own volume, but when it is floating, it will displace liquid equal to its own mass or weight. So that is the difference between when a body is fully submerged or when a body is floating. Okay, so we can use this thing in order to answer a few tricky questions you might have already heard about. So one question I'm going to mention is, like, first, say for example there is a boat and that is floating in some small pond, and there are some chunk of stones kept on this boat. Okay, obviously the density of stone is greater than the density of liquid, but as these are kept on the boat, the whole system is floating on the water, let's say. So the question here is, so right now it is in equilibrium, this system is in equilibrium, the boat stone system. So if we start throwing the stones into the river or into the small pond, we must say, so what will happen to the water level of this pond? That is the question. Okay, so the answer to this is very, very simple. Okay, now you see, like when the stones are on the boat and are floating, so at that situation the stone are displacing liquid equal to its own mass or its own weight. Okay, so but when they are thrown into the liquid over there, now they will be submerged and they will be displacing liquid equal to their own volume only. So previously they were displacing liquid equal to their weight, and finally they are displacing liquid equal to their volume. So obviously the liquid equal to their weight would be greater than the liquid uh, uh, equal to their volume. So previously they were displacing more volume and finally they are displacing less volume. So the level will go up. So I hope you have understood. Just by comparing the final and initial situation, and what we will be comparing, that in initial situation, how much liquid the stones were displacing, and that will be equal to their weight, and in final situation how much liquid the stones will be displacing, and that will be equal to their volume. So obviously the level will go up. The second question of the very same nature I want to discuss over here very quickly. Let's say in a beaker there is some water, and say ice cube is floating, an ice cube is floating on that water. As we understand, like density of ice is less than that of water. Okay, so it will simply float on the surface of water, and it would be partially submerged and some part of it will be outside the water. Okay, so now the question is, if this ice cube melts, if this ice cube melts, what will happen to the level of liquid in this container? And answer to this is again very, very simple. We must try to compare before and after situation. So before melting, when the ice cube is floating, it is displacing liquid equal to its own mass. Okay, before, again I am repeating, before uh, melting, it is displacing liquid equal to its own mass. But when it melts away, what will happen? It will get converted, the ice will get converted into water itself. Okay, so how much water it will get converted into? It will get converted into the water of same mass as the ice was having. So now you see, the previously this ice was displacing this much liquid. Okay, so this, on this part, on this region, there was no water previously. So but when the ice melts, okay, the mass of the ice will be equal to the mass of water that has been created, and that obviously is going to occupy the same volume. So the level, you must say, the level of water in the container will not change. So that is another example. And now let's look at the equilibrium of the floating body. Now you see, equilibrium of floating body. So now one very simple analysis we are doing. So let's say this is some solid and which is submerged, which is floating in some liquid. Let's say the density of liquid is rho L and density of solid is rho S, and its total volume is V, and the submerged volume is V dash. Let's say submerged volume V dash, we must say that is submerged volume. So what we wish to find out, the fraction of submerged volume, this quantity we wish to find out. Like what fraction of submerged volume of the total would be there. So this we can do very simply. We just have to look at the force balance. So the force balance will be this floating body will be experiencing its weight will be equal to simply rho s into v into g, and it will be experiencing buoyancy, and buoyancy will be equal to weight of displaced liquid, so that is rho l. And now you must realize it will be displacing liquid, the volume of displaced liquid will be only v dash, that will be equal to the volume of only submerged part, so rho L V dash into G. So as I have already stated, so this floating body will be in equilibrium. So this quantity here and this quantity here are going to be equal. B is going to be equal to W. So B is rho L V dash into G is equal to rho S V into G. So this will simply give us V dash by V will be equal to rho S by rho L. Okay, so this quantity we are able to find out here. Okay, so this is one very simple relationship. Here we have only considered the translational equilibrium of this floating body. Let's discuss one case when we will be looking at the rotational equilibrium of the body here. So let's have the stick in water problem. Stick in water problem. So let's say we have some beaker which is filled with some liquid of density rho L, okay, up to a height of h. And there is a stick of uniform cross section and length L is hinged at this point over here. Let's say this point is O. Okay, so let's say this is the equilibrium orientation of this stick, and let's say at this orientation it is making an angle theta with the horizontal over here, and let's say density of the stick is rho s and it is of uniform cross section. Okay, we wish to find out the value of theta. Theta here is unknown and we wish to find out the value of theta. So here we must learn about something called center of buoyancy. We have already understood about the buoyancy, that would be the force exerted by the liquid on the submerged body. Okay, so but what would be the point of application of that buoyancy? Whenever we are going to consider the rotational dynamics, we need to understand what would be the point of application of any given force in order to calculate torque. So here the point of application of buoyancy you must see, that is due to the weight of displaced liquid. So you must understand, like this part of the stick is submerged and here like this part of the liquid has been displaced. So the center of buoyancy would be nothing but the center of mass of this submerged part somewhere here. Let's say this length, submerged length is L. So this length would be equal to L by 2, you can see, and the buoyancy here that would be acting in vertically upward direction. And similarly, the another force that would be acting is obviously its weight, and the weight would be effectively acting at center of gravity over here. That would be the midpoint of this stick, and this here will be its weight. Okay, so we wish to find out, Like under the condition of equilibrium, what would be the value of theta? Obviously the torque due to buoyancy is in anti-clockwise direction, and torque due to weight is in clockwise direction about this axis of rotation. So for rotational equilibrium, these torques must balance each other about this axis of rotation. So what we must say, like what would be the torque due to weight and what would be the torque due to buoyancy, we must equate it with each other. Let's first write down the values over here. So torque due to uh, the weight. So the weight, first of all, the magnitude of weight would be rho s is the density of solid, and let's say a is the cross sectional area of the stick, and that multiplied by the total length would be the total volume of the stick, and this is the total mass of the stick, and that multiplied with g would be its weight. So this is weight we have calculated over here, and its arm, you must see, this would be its arm. So this hypotenuse is capital L by 2, you can say, and its cos component cos theta. So this term which we have written is torque due to its weight. Now equal and opposite will be the torque due to buoyancy. So how much will be the buoyancy? So buoyancy, you see, will be equal to the weight of displaced liquid. So the density of liquid is rho L, and the displaced liquid, the volume of displaced liquid will be only this part over here. So that is its length, cross sectional area is same, and its length we have taken it as L, and that multiplied with G would be nothing but the buoyancy, and that multiplied with this arm, this length over here. So this is small l by 2, so this is small l by 2 cos theta, you can say. And it is very good to see that a lot of things are getting cancelled. For example, a and g are getting cancelled, this 2 is also getting cancelled, and this cos theta is also getting cancelled. So what we will be getting by rearranging L square by capital L square is going to be rho s by rho L over here. So what we can say, that small l by capital L is going to be root under rho s by rho L over here. Okay, and we wish to find out this theta over here. This theta just we needed to find out. So theta here we must understand, see, looking in this right angle triangle, or this right angle triangle over here, this hypotenuse is L, and we wish to find out h. So h, this small l can be written as h by sine theta. H by sine theta by L is equal to rho s by rho L, and just by rearranging you will be getting the value of sine theta, which would be rho L by rho s into h by L over here. So that is our answer. Okay, so now let's discuss one more concept, that is the concept of metacenter, and that would be necessary in order to decide the equilibrium of floating bodies, whether the equilibrium is stable or unstable or neutral. So now you see, let's discuss the equilibrium of floating bodies for its stability. Okay, so there you understand there are three kinds of stability. The first one is stable equilibrium, and the second one is unstable equilibrium, and the third one would be neutral equilibrium. Neutral equilibrium. So let's say we have some, let's say some body of this shape, let's take. Okay, and this is floating in some liquid. So obviously this is in equilibrium. So we wish to investigate what type of equilibrium that is, whether it is stable, unstable, or neutral. So what we must do, we must look at the forces acting on this. So you must understand, like for example, the center of gravity is here. So its weight would be acting somewhere in downward direction, and say center of buoyancy would be somewhere here. So the buoyancy would be acting in vertically upward direction effectively. So right now this is in equilibrium. So you can see that the net force will be equal to 0, that is W is equal to B. And also, okay, this W and B are not producing any couple. Okay, so the net torque is also equal to 0 on this body over here. So that is in equilibrium. Okay, so depending upon how we disturb this floating body, we can check whether the equilibrium is stable, unstable, or neutral. Let's say, for example, we displace it horizontally. So you can see